Hello everyone, we are Project Batch 25 of Computer Science Department, MIT Mysore. In this video, we are going to walk you through a major project that is automated water flow management and crop prediction using IoT and machine learning, which was done under the guidance of Professor Prasanna Patil. Before we proceed, we shall introduce ourselves. I am Uday Panindra Chowdry.
I am Rajath Y N. I am going to discuss about IoT demonstration part.
I am Prajwal N P. I'll be speaking about crop prediction part.
I am Chaithra and I'll be walk you through the algorithm.
These are the contents which we are going to discuss in the first part of this video. That is introduction, literature survey, design details, existing system, proposed system, methodology, results, and then conclusion. And moving on to introduction. As we all know that India is the second most populated country in the world, consisting of one-fifth of the world's population. And agriculture is the backbone of Indian economy. Agriculture is the primary source of livelihood for about 58% of India's population. And over 70% of Indian population depends on farming, either directly or indirectly. And water is the main resource for agriculture. And 82% of India's water is used by agriculture. And over 4% of that water is being wasted. Hence, we are proposing a system model to reduce the wastage of water that reduces the problem of water scarcity. Coming to problem statement, it's becoming a complex issue for farmers to manage their crop cycles due to scarcity of water and labors. This is because farmers have to visit the farms repeatedly to see whether a particular plot has received adequate amount of water or not. If completed, they have to change the water flow to the next plot. And due to the lack of knowledge about what crop has to be grown that yields more profit, farmers are facing financial problems. This is because they produce crops more than the present day demand in the market. Hence, to reduce the manual work of the farmers, we are developing a project to modernize and to reduce the problems faced by agriculturists using IoT and machine learning techniques. And the solution for this, for few of these issues are: in the proposed system, the user can relentlessly monitor the water level in both the reservoir and the farm field remotely on a mobile without visiting the farm. And our system would turn on the motor when water content in the soil goes below a threshold level, and it would automatically turn off the valve when a particular plot has done with watering and directs the water to the next plot. And implementation of ML techniques helps to predict the crop and provide profitable crop information. And based on the crop, we also provide the details about what amount of fertilizers are required. Moving on to literature survey. There was an extensive literature survey done. Many papers related to our project title were studied and important information was gathered. And we found out that the existing surface irrigation system is not automated. And many machine learning techniques were used to predict crops, and crop yield are having reasonable error rates. Thus, we are using decision tree algorithm to predict the crop. Now we'll discuss about our design details. In the architecture shown, we have divided a piece of land into 3 plots, and we also implemented water sensor, moisture sensor, temperature and humidity sensor in all the 3 plots. The values are recorded by these sensors and are sent to base station using RFID through cloud database. In base station, we trigger water motor pump from the obtained values to water the plot, and the valve is set automatically when the required amount is met. We also use water sensor to know how much amount of water has been flown through that plot. Along with the water sensor, we also forecast weather using API protocol of the plot. Existing system. In the existing system, everything is manual and time consuming. Farmers have to visit the farm and direct the water flow to the next plot every time when the plot is done with watering. And they also face problem for labors to do the work manually. Farmers are farmers are unaware of the amount of fertilizers to be used. This is because if the farmer uses pesticides that exceeds a certain level, then the crops may die or may produce less yield. So in our proposed system, the user can continuously monitor the water level in the reservoir and in the farm field remotely on a mobile or PC without visiting the farm. The task of switching the motor on and off has been automated. Our system would turn on the motor when the water content in the soil goes below a threshold level, and it would turn off the motor when a particular plot is done with watering and directs the water to the next plot. And we have implemented ML techniques which helps us to predict the crop to be grown, which yields more profits. Here we collect info of what crops are being grown in a specific area so that farmer can grow a crop which is produced less in the specific area. And we also provide information about the fertilizers to grow a particular crop. Methodology. This will be explained by Chaithra.
Let me start what basically K-means algorithm is. This is an iterative algorithm which tries to partition dataset into K predefined distinct non-overlapping datasets, that is clusters. And usually the algorithm works as follows, like step 1 would be the selecting number of clusters, step 2 would be randomly selecting 3 distinct data points, then measure distance between each point, assign points to the cluster and calculate the mean. And in here, in our project, this is how it goes. Step 1 is creating data frame using 2-dimensional data set with available sensor values. Sensor values are like moisture sensor values, DHT sensor values, all those values are collected and 2-dimensional data set is formed. Then we find the centroid. To find best cluster, we'll have to compare it with other clusters also. So for this situation, we'll assign 3 initial clusters which are previously stored in the local database. Step 3 would be randomly assigning data for cluster. This completes the cluster centroid. Step 4 is reassigning each sensor value to nearest cluster centroid. That is recomputing the centroid for clusters to get precise value for that. The next step 5 is repeating step 4 until there is no variance, like there is no alternative values. Till then we'll repeat the step 4. Once there is no further value to trigger the pump for successive repeats, this will mark as termination of motor. That means the motor will be turned off. This K-means algorithm is used in the IoT part, as I explained now. The next method algorithm we have used in our project is KNN algorithm. KNN algorithm, it is a super simple way to classify data. Like we'll start with the known categories data set, and in each case of different data, we'll cluster it, then add a new data, which is an testing data. We'll try to classify it based on the previous data. That's how KNN works. And in our project, step 1 would be the load of training data as well as testing data. Testing data would be the current data value which is currently coming from those sensors, and the training data are the values from the sensors which was previously stored or recorded. Step 2 is choosing the value of K, which is taken from test data, and this acts like a centroid point. Step 3 is for each point in the test data, we'll first calculate the distance between test data and each row of the training data. And now this is done with the help of Euclidean distance. There are many other distance formulas to calculate, like Hamming distance, Euclidean, Manhattan. But this Euclidean distance works well in this case, so we have used Euclidean distance. Next, based on that distance, we'll sort them in ascending order in array. Choose top k rows with from sorted array and assign that class to this point, test point. This is how, and then we'll end it. This is how KNN works.
Coming to results, this project deals with water management in agricultural fields and prediction of crops based on the location, weather, and other values. The developed model reduces the manpower required for agricultural works. Moving on to conclude. Through our system model, farmers can view the farm activities in their device by logging into the given URL. He can view which plot is being watered, and he gets the moisture level values of each plot. The user can specify a particular location to predict a profitable crop. And installing smart irrigation system saves time and ensures judicious usage of water. Moreover, this architecture uses microcontroller, which promises an increase in system life by reducing power consumption.
Hello everyone, I am Rajath Y N. I am pursuing my BE in Computer Science and Engineering at Maharaja Institute of Technology, Mysore. And today, me and my teammates are here to demonstrate the working model of our final year project titled as Automated Water Flow Management System and Crop Prediction using Machine Learning and IoT under the guidance of Prasanna Patil. Basically, India is an agricultural country where more than 60% of its population depends on the agriculture. So in the present era, 80% of the fresh water is being utilized for agricultural works. So our model works on overcoming the sensors in the agricultural fields, so that water is provided to the crops. To start off with the hardware part, this is the demonstration setup of our project with 3 plots, which consists of 3 plots and one base station and motor. So these are the components. Each plot consists of an capacitive soil moisture sensor version 1.2, and it consists of an DHT11 humidity and temperature sensor, and it consists of an Arduino Nano, and it consists of an NRFZ24L01 sensor, and it consists of an relay. The moisture sensor is used to detect the moisture level in the soil, and DHT11 sensor is used for determining the temperature and humidity of the soil, and the relay is used to turn off the solenoid on to automatically turn off the solenoid on and off, and NRFZ is used as a receiver to receive the information from all these sensors, and the node. So the RF module acts as both sender and receiver. It collects all the information from the different sensor connected to it, and it transfers the received information to the base station. So the moisture sensor, all these components are connected to the nano board. So the moisture sensor is connected to the nano board of port A7, and yellow pin is used for signal transmission, and red and black are used for voltage pin, which runs at 5 volts. And next, the DTH11 is connected to the port D3 port. Is connected to the D3 port, and this is the RF module which has 7 pins, which has 7 pins, which is connected to the nano board from D9 to D13 ports, and it is the relay. Relay is connected to the port D5, and relay is used to turn on the solenoid automatically. The same connection is similar to all the 3 plots, and it is the solenoid which is used to turn on the valves on and off, and it is the flow meter which is used to determine the amount of water flowed per second. And it is a base station, and it has an RF module and node MCU, and it also has a nano board, and it has a relay, and it has a local weather station which displays the weather of a particular location using a LED screen, and all the information transferred from the plots are transferred to the nano board of the base station, and based on that values, a relay triggers. The relay is used to turn on the motor on and off. Connection part goes like this, and the relay is connected to the solenoid, and the red wire is connected to the positive terminal, and the black is connected to the negative terminal, and the nano board is connected to the flow meter. We have to match the color series in both sides, that like red, yellow, black. Here also red, yellow, black.
As my teammate Rajath explained how these components are connected and work, now I am here to show or demonstrate how our project actually works. These are the 3 moisture sensors which are already dipped in the water, which means they are humid now, which means that they have some water content. All these different plots have different threshold values in moisture sensor, because if we grow different crops in different plots, then they require different temperature or moistures. So we have set different threshold values. Plot 1 has a threshold value of 70% of moisture value, and this has 50% and this has 30%. It consists of 5 different values for each plot. Plot 1, plot 2 and plot 3. The different values are water flow rate, while the water is flowing, at what liter per second the water is flowing, and the total liquid flow. This is like if the motor is suddenly turned off, when the water is flowing and the motor is suddenly turned off, and again it goes back to on stage. But then if the water is already filled with 50% of water and you have to fill only the rest 50%, this helps because it stores all the pre-data, how much water was flowed previously before the motor was turned off. That data is stored here, and then when the motor is turned on, this data will go on adding, so you don't have to start it from the beginning. The temperature, humidity and soil moisture sensors, which I've taken from DHT and soil moisture sensors. Here you can see the motor status, which is white in color, which means the motor is turned off. When the motor is turned on, it changes to yellow. Once this moisture sensor is out of water, which means there is no water, no humid, and when the relay activates the solenoid, first you will have to activate the motor for the water flow. This how it works. The RF module in this plot 3, this collects the information of all the different sensor values along with flow meter values. This acts as a sender RF module, and this RF module in the base station that receives all those values and sees that the moisture level is low and you'll have to turn on the motor, and that's how it triggers the motor. The water flows to the crop. We have changed the container which has no auto value. So soil moisture you can see here as 2%. Since it's less than threshold value, we'll turn on the motor. Water starts flowing, and once it reaches the threshold value, the motor will automatically stop. The motor has stopped because it's taking a bit time for the soil moisture. But here the relay has changed its green value because, which means that this moisture has reached its threshold value. That is why the solenoid is turned off. Look here, the soil moisture is changed to 49%, and hence automatically the motor is turned off. This is a demonstration of plot 1, which has the threshold value of 70%. With this here, the moisture sensor is already dipped in the water, so it means the threshold value is more than 70. As you can see there, the moisture is already 100%, and hence the motor status is white in color, which means it's turned off. And liquid which is flowed is 0 ml because there are no previous records of flowing water in this plot, and hence it is 0 ml. Then we take this moisture out of this water bowl, place it. This has activated relay, which means it activates solenoid. This solenoid. Now let me place this in an empty container. Since there is no moisture, the motor is triggered. Since it takes time to reduce moisture in an intense, it's taking some time. So once this moisture sensor is below the threshold, once it is detected, the motor automatically turns on. You can see that the motor sensor value is 16%, which is below threshold, below 70% of soil moisture, and the water is flowing from the motor. And once it reaches the threshold value of 70%, the motor automatically turns off, as I said earlier while explaining the working of plot 3. The motor is turned off because the moisture has reached the threshold value, but it's taking some time to update. But as you can see that the flow of water is 93 ml per second, which means that data will be recorded, and once the motor is again turned on, the addition of that flow of water will goes on adding to that previous data. You can see that the threshold value is 70%, but it has already reached 82%, and hence the motor is turned off, and the ml is 2805 ml. That amount of water is already flowed through this plot. Let me do this again so that you will witness the addition of data of flow of water. Once this capacitor, this sensor is again taken out, which means the moisture sensor is low, the water goes on flowing, and again when it pushes out, since it reaches the threshold value, it's down, the motor is off now, but you can see that the water flow is added, which is not started from the beginning, but it goes on adding to the previous data. Previous was something 2085 in figures, and now it is added with 2000 something. With considering soil here, to precisely calculate how the soil moisture sensor works. First, it's humid now because it's in the water, but once I take this out of water, the relay is triggered, and let me place it here. The relay is still triggered because this is dry soil which is not moist, and hence the motor turns on. 1 second. Since we have less data, the motor changes from off state to on. It's changing here, the percentage is changing from 26 to 28. And once it reaches the threshold, it's gonna stop. It has reached here, which is 70%, which was the threshold, but it has already reached 79%, 90%. That is why the motor state is off. Reserve it oil. Whenever the soil becomes moist, the motor turns off.
So for crop prediction purpose, we use machine learning, and we need XAMPP and Visual Studio. First, we need to open XAMPP and start Apache and MySQL. After that, click on admin button. You get the database. And this is the database, crop predict dbk. Click on that. And we use two tables, crop new data set and crop user data. Here we have stored the data sets for predicting the crop, and this is the user details. The user one and who gets registered, that his details will be stored here. After that, open Visual Studio. These are the set of code. So click on user home. We used HTML and C#. This is the user home code. Press Ctrl 5 to run the code. And you get the home page. Click on register here. These are the credentials that you need to enter for registering: your name, your email, mobile number, password, re-enter your password, and you need to enter your address. Click on submit. You get a trigger message saying that registered successful. Click OK, and you can see your database, user data. See, the registered user details will be stored here. You can log in here by entering your email. Click submit. Here you'll get a prediction page where your Google map is displayed with the help of Google API. This is the location. It automatically detects your location. It keeps tracks of your page. This is the latitude and longitudinal values. You need to enter your area acres inland, 25, soil pH values 7, and once you press on analytics button, you'll get the crop predicted crops. These are the predicted crops, and you can see the crop name, investment per hectare, profits, seeds per acre, fertilizers per acre, approximate investment. These are the attributes that we are taking for displaying the output, and these are the crops that you can grow in the location: Mysore, sugarcane, and fertilizers per acres is in kg, 50 kgs, 54 kgs. And you can grow sugarcane, cotton, paddy, black gram, ragi, groundnut, and finally you can. This is the chart overall crop revenue, and this is displayed with the help of Google Charts. And we use k-means and k nearest neighbor for predicting the crop, and SVM for classification. And this is the final output. That's it.